thank you, Orange, and the afternoon review. My report is processed in CMTF oxygen carrier research at Tsinghua. This project is collaborating with Ingrid and Joanne from CTech Lobby. So my presentation includes 3 seconds. Testing in microfood test at GTA for multi-cycles, reaction kinetics of CMTF and manufacture CMTF at a larger scale. So first we developed a new experimental method to test CMTF oxygen carrier. As mentioned by Professor Lee, the principle of the new method is microfood test by the thermogravity analysis. The principle of this instrument is measure the on-time test change under the fluidization stage through switching the gas between oxygen and hydrogen or methane. The oxygen carrier reaction with the agent to change the mass. First, we test the long-term redox stability for CMTF. We found after more than 1,000 cycles, the CMTF particles still hold its fluidization and without any agglomeration, even without the fluidization gas. There are interesting findings. The oxidation rate of CMTF is very fast, and CMTF can finish the full oxidation within just 4 seconds. So that means the air reactor just needs a very low pressure job because the needed bond inventory is very low. Also, CMTF can finish the reduction by hydrogen within 30 seconds. Phase 2, the CLC application. We manufacture CMTF at a large scale. We use the commercial chemistry to produce CMTF for reducing the cost. The raw materials was made into styrene in the mixture, and then the styrene was bound to the top of the spray device. Then the droplets formed by the styrene, joining by the hot air in the spray device. The particles were formed in the bottom of the spray device. We can control the spray temperature and the properties of styrene. The satisfied particles can be manufactured. We find there are more than 9% particles is in the range of 75 to 500 micrometers. The whole cost, including purchase raw materials and production, also include cancellation fee, is lower than $2,000 per ton. Finally, we evaluate the bonding inventory and the fan power if we use CMTF as oxygen carrier in an actual CLC. We find top of the kinetics of CMTF is very fast, so the needed bonding inventory is the lowest, which is far lower than that of armalite, manganese, and copper. In the result, the fine power of air reactor and fuel reactor is the lowest, which is 3 to 3.5 lower than that of other oxygen carriers. In conclusion, CMTF is a very good oxygen carrier without any agglomeration during non-redox cycles. CMTF can be fully oxidized just within 4 seconds, which means no pressure drop in air reactor. Outstanding production of CMTF perovskite was successful realized. Finally, CMTF has great potential to decrease the oxidation cost due to the lowest fine and energy consumption. Thank you.
Okay. Yes. So some short overall summary from this presentation and this work. We have been in the CHEERS project developed and validated 3 relevant oxygen carrier candidates for the demo unit. This has been done in close cooperation between Chinese and European partners, and this has been a necessity to achieve these results. This is not, this is real cooperation, operational cooperation, where we really need each other to get what we need. But in the end, we selected the ilmenite T2 because of several criteria. It has an acceptable reactivity and performance. It is sulfur tolerant. It is matching the demo unit particle size requirements. And it also have a lifetime and cost and availability, which is good. And we also see that these agglomeration issues can be solved by correct pre-treatment of this ilmenite. So it has been pre-calcined in Daean before operation. And with some steam addition and careful fluidization of low velocity zones, we can manage that. In addition to the 2 natural minerals, we have the synthetic CMTF perovskite, which we also see as a very promising candidate, and especially maybe for low sulfur fuels. And fuels low in ash, so we don't lose too much of the oxygen carrier. So, we have therefore shipped 250 tons of this ilmenite from Titania, as in Norway, to Daean. You see the picture here when it arrives. 90 tons for the Chinese configuration and 160 tons for the European configuration. And here we have a material cost of 320 euro per ton. That's about $300 US. And on the last slide of the relay, we saw nearly $2,000 US per ton for the CMTF. So there is a huge cost difference, but it's also a huge performance difference. So, but for the CHEERS project, this is the one we will start off with. Yes, thank you very much.
Thank you, Eivind and Heidi, for a very nice presentation. Are there any questions for the presenters? Yes, please. Thank you.
Thank you for the presentation. What are the main drivers for the cost? Can we expect a decrease of the cost, especially for the synthetic oxygen carrier?
Yeah, I can start with the ilmenite, which this is the price that Titania get on the worldwide market, and they are shipping regularly 30,000 tons to China. So this is a trade that so we can just follow those choices. When it's related to the CMTF on the synthetic materials, I would say I really don't know exactly what is the, you have to know which is the highest cost of the CMTF, which is it raw material or is it calcination?
We may manufacture CMTF using the commercial chemistries to introduce the elementals such as calcium, magnesium, iron, and TR. Yeah, this is the first cost, and then the second cost is the spring journey. Spring journey, we find a factory. We find a factory to produce the particles. So we should spend some money for the electric, for fuels, for people, for workers. Yes. So this is the second cost, and the third cost is cancellation. Yeah, cancellation we found. We also found another factor to cancellation CMTF particles in our clinic. Yes. So we also need to spend some money for electric fields and workers. And the first cost is transport, because we produce CMTF far away from Beijing, from Chengdu, from there. So we need to transport the CMTF from other area to Beijing to there. So the totally cost we evaluated is near to $2,000 per ton. Thank you.
I think Ingo also wanted to comment on that.
I should maybe comment that the seeding and pre-treatment done in China has not been included in that price. So it's a cost. And also when it comes to manganese ore, we're talking about if you need to heat a lot of manganese ore, crush it, so we use all the fractions. Also the mass should be the right fraction, meaning that you have some more also such things as starters, this is fully easy, depending on how much heat is heated by the people actually shut it on the waves. But that is for the CTF strategies for the rest.
Just a comment. I think the transport cost is one major one. And for the ilmenite, I just showed you the material cost. However, that was 320 euro per ton, but the transport beyond was 250 euro per ton. So that is a very important component for sure.
And any more questions? Yes, over there.
During the operation, how is this, how to say, media will be lost, after the several cycle usage. How about the loss of this media?
Yes, thank you for that question. I should probably have mentioned earlier, because that is of course an issue for CLC. Your spent material after use has to be disposed. When it comes to ilmenite, it's a natural ore, it's a natural mineral. It is rather easy to dispose this material. It can be used for, at least for some fillings or different kind of purposes. It's not as special or a hazardous waste. and neither the CMTF is a hazardous waste. But for example, early CLC tests were done on nickel oxide, and then you have more problems with this. But it's an important thing to consider. And for example, ilmenite, we are evaluating if the spent ilmenite could be taken back to the ilmenite processing to process it to titanium dioxide. It might be difficult, but it could be an option. But it is rather easy to handle the ilmenite after use.
More questions? Yes, Inga.
And we should also the lifetime, which is of the part that cost as well. And it's not accepted, but lifetime is important.
You want to comment on that, or? Okay.
I think the lifetime of the ilmenite is some 100 hours. We have conservative estimates when we made a note for the test, saying a lifetime between 200 and 500 hours. Earlier projects can show ilmenite lifetime of about 500 to 700. So we are in that range. That means that we'll have to, for example, refill the whole unit, the inventory in 500 hours. But it will be just a small maintenance flow in any case.
So that time for a question, if there is no. I just have one quick last question then. We saw that the CMTF is more expensive, but as I understand it, you need somewhat less of it in the reactors, and also the lifetime is much longer. Have you made any studies on cost difference and the total cost difference when it comes to as the years pass?
But I have to be seen, we have not taxed the CMTF for this CMTF, especially for small scale CLC reactors, because after tax we just do how now it's enough time. But we tax the particle streams in the lab according to ASTM standard. Is D5757. The particle strength is I think it's enough. So I think its lifetime is enough for real CLC technologies.
Yes,
Yeah, I will answer to your question. For CMTF, we think two methods to control the cost. First one, we want to use this material to biomass or natural gas chemical conversion, not for coal. For coal, there are a lot of ash, the material must be lost. So the cost for material, CMTF material is high, so we cannot use it in high ash solid fuel. So in our plan, we want to use CMTF in low ash biomass or natural gas. For this case, the powder, the CMTF powder can be collected by the back filter in the end of the flue gas. And the powder can be used again for the preparation of the fresh CMTF. And this not a real loss of CMTF material. So we can put them back together for the redraining material preparation. So in this, the total cost will be reduced, not real loss of material. Okay.
Yes, thank you. So then I think we are pretty much on time for a tea break. So I will thanks once again the presenters from this session for their presentations. And we'll convene here again ready to start at 16:05. So 5 minutes past 4, you're ready to start here.